Welcome back. So last lecture we have seen different approaches to optimal control. Optimal control is where we minimize some kind of cost and obtain a feedback control law or open loop control law, right? In the open loop approach, we use this calculus of variations approach, and we ended up with basically solutions requiring in terms of solving some kind of boundary problems, initial value in some case, and then the Lagrange parameter had the final value, and then we have to use this shooting methods, and then that's a very difficult thing to do, but at least for many of the problems people have been using well-known numerical methods to solve those things. The problem of course with that approach is it's quite sensitive to any uncertainties of either parameter or disturbances and things like that. So it works very well for the standard example that I kept talking about is basically sending some space shuttle from here to outer space somewhere, right? So once you're outside the atmosphere, Earth's atmosphere, then basically things are much better in terms of disturbances or anything like that, right? So it works very well. I mean, we can actually optimize exactly what we want, and then we can solve the problem and decide control at every single point, and there's no uncertainty, so we can implement that particular control constraint of stability. So we provided a solution which gives controllers that are stable and minimizes a cost over the infinite horizon, 0 to infinity, and it depends on again some kind of function called Hamiltonian, and it has to satisfy two of those things. But then typically we expect stability to be there in the cases where we expect disturbances or some kind of unmodeled uncertainties, and therefore these controllers that we are designing are best if they are not too sensitive to uncertainties. So therefore it's understandable that we expect some kind of stability margins, and which is the topic of this particular lecture. And then even back in the classical control, beyond stability, the first thing that they specified in terms of a design specification is stability, gain margins and phase margins and things like that. So in that fashion, basically we will try to define first, first show, actually demonstrate how gain margins work on a particular type of couple of examples, and then define more general notions of stability margins, and then show results for those, right? So let's remind ourselves how this optimal feedback control works. So we have the standard dynamical system x dot equals f of x comma u, and then we have this cost defined in terms of this function L, right? And of course the problem of optimal control is simply find the best possible stabilizing control, and then in terms of feedback function. The solution depends on a bunch of conditions. The first few of them are simply something to do with your standard Lyapunov conditions. V has to be a Lyapunov function satisfying, of course, the V of 0 is 0, V of x is positive definite, and V of x times f is strictly less than 0 for non-zero x. That gives the stability part, right? But if you want the optimality part, then we have to satisfy these two conditions. At the optimal feedback control, the h function has to be equal to 0, and at any other value for u, the control, it has to be non-negative, right? And so h is given by this L plus P transpose FU, right? So this is something that we have seen last class, but I'm going to demonstrate now on a very simple example to see how one uses these two conditions to get answers for solving for phi, v, and all whatnot, right? So I'm going to consider this very simple scalar nonlinear system, x dot equals x square plus u, and then again a cost is very simple in terms of basically it's going to be a quadratic cost, and in this particular case h becomes this x square plus u square plus p times x square plus u. So I'm going to basically go back to my handwritten notes and then see what happens to this function h, right? So I have this h of x comma u comma p as x square plus u square plus p times x square plus u, right? This can be rewritten as u square plus pu plus some function of x, purely a function of x, okay? So this is clearly a quadratic function, so it will have a minimum. It's a convex function for that matter. They take the second derivative, we will get 1, and that is a sufficient condition for strict convexity. And of course the simplest thing to do is basically treat everything as constant and set the first derivative of h with respect to u. That's the nice thing about convex problems. Basically, you'll get 2u plus p is equal to 0. So indicating that basically for this particular function, u equals minus half p as your minimizing value, right? So therefore, I'm going to basically h comma minus half p comma p, substitute for u in this. I'm going to get the minimum value for this. So minus 1/4 p square, 1/4 p square minus half p square plus 1 plus p whole square. And so when I substitute the optimal value into this, I'm going to get this 1 plus p whole square minus 1/4 p square, right? Of course, we know that h of x comma u comma p is going to be greater than or equal to h of x comma minus half p comma p. So the difference between these two has to be greater than or equal to 0. In fact, one can see basically x comma u comma p minus h of x comma minus half p comma p, the value at general u minus the optimal value, this cancels this, and then u square plus pu plus 1/4 p square, which is nothing but u plus half p whole square. Okay. So what this means is h of x comma u comma p is equal to this u plus half p whole square plus h of the optimal value, right? Now, if you recall, basically the Hamiltonian, we need to satisfy that at the optimal value it has to be 0. So I'm going to set this to 0 with p equals v prime, right? And then this is automatically greater than or equal to 0. So satisfying both these conditions. So I'm going to repeat this logic again. So I have this Hamiltonian function, right? I find the minimum value, right? And then the this happens to be convex, but in general it may be a little bit more difficult. But let's say we manage to find the global minimum of this h. Basically, you can rewrite the Hamiltonian, the general Hamiltonian, as some non-negative function plus the optimal value, right? And if I set the optimal value is equal to 0 for p equals v prime, then essentially what this means is h of u comma v prime is going to be greater than or equal to 0, which are the two conditions we need to satisfy, right? So this is a standard technique that we need to employ when we solve these problems, right? So in fact, that's exactly what I have it here. So h of x comma u comma p is this non-negative quantity plus something there, right? So I'm going to set this particular thing to 0. So we'll get an equation. The other part is basically simply satisfies non-negativity, which we want anyway, right? So this is the equation that we are going to depend on actually deriving for v prime to start with. From v prime we can get v of x, and once we get v of x and v prime, of course we can get u equals minus half p, right? Which happens to be minus half v prime. So anyway, solving for this, we get v prime, and then basically we already can get optimal controller, but we need to ensure that the v of x is actually a Lyapunov function. So we need to solve this. This is a differential equation in x with the boundary condition v of 0 is 0, because that's the condition that we need for it to be a Lyapunov function, and v of x is going to be like this. So clearly this is v of 0 is 0. It's not as obvious if it is positive definite for all non-zero x, and then I'll leave that as an exercise for you. And essentially basically v prime, if I put basically minus half in front of it, basically will be the optimal controller. Okay, so now I'm going to basically look at the sensitivity of this controller. So for which what I'll do is u is equal to some parameter, gain parameter, times the optimal controller that I obtained, right? I should have given the value of optimal controller here, but v of x is basically minus half v prime x. Then I can show something very interesting. For all these values of alpha greater than or equal to half, Okay, we'll see what happens. I'm going to compute V dot for this particular U, the scaled version of the optimal control. V dot is nothing but V prime times F plus GU, where G is 1 in this particular case, U is alpha times phi of x, and of course phi itself is minus half V prime, right? And I can manipulate this in such a way that I can write it like this. So if you recall, this is nothing but the Hamiltonian equation, or the equivalent of your algebraic Riccati equation in linear systems, and that's 0. We know that it's 0. V prime satisfies this particular equation when it's set to 0. So what we will end up with, basically V dot is strictly less than this particular quantity, which is always going to be less than or equal to 0 for all alpha greater than or equal to half. So what does this mean? Not only this phi of x is stabilizing controller, but if I scale it, let's say alpha equals 1, of course, is what we know, it's stable, but I can go up to half in the below, it's called downward gain margin. Basically, we can keep multiplying it with factors that are less than 1 up to half, right? And then on the upside, upside gain margin is infinity in this particular case. Basically, it can go up to infinity, any number multiplying this thing. So that's a fantastic observation for any optimal control that satisfies certain conditions that we have seen, will give you a gain margin of half and infinity, right? For the particular cost we chose and things like that, right? So anyway, this is for a very simple example, but we can actually generalize this observation. In fact, identically goes through when it comes to this particular example, where I'm going to consider my system to be affine in control. So x dot equals F plus GU, and I'm going to choose my cost to be L1x plus U transpose R2 of x times U, where R2 is positive definite. I don't say it here, but L1 is also non-negative. So we have this two costs. Let me remind you, basically these cost functions are chosen in such a way that we want to weigh both the state as well as the control. In this particular case, we are weighing the control as a quadratic function, whereas L1 could be very general, right, as long as it's non-negative. So the Hamiltonian is going to become L1 plus U transpose RU plus P transpose F plus GU, right? So again, this is a quadratic function in U. If you treat x as constant, then basically we can find the minimum for that, and at the minimum we are going to set that to be 0. That's like your Riccati equation, and the other part is going to be non-negative. So do the same thing as we have done before, right, by setting first derivative to be 0, and then basically substitute that into that, and then manipulate, and we'll get these two parts, one quadratic non-negative part, right, and the second one is basically the one that we want to be 0, right. So again, the same conclusion. If this particular part is actually made 0 at V prime, then this phi becomes your optimal control, because it satisfies both the conditions. H of x comma phi comma V prime is 0, and then of course H of x comma U V prime is greater than or equal to 0, right. So in this particular case, of course, it's a very complicated equation. Again, it's a quadratic equation in V prime. We hope vector quadratic equation for that matter, and then let's say we know how to solve that, and basically and then the integral, the V function is going to be satisfying your Lyapunov conditions, right. So we're going to make further assumption that L1 is actually positive, not just non-negative, and look at its robustness properties. U equals, let's say again the same trick, alpha times phi of x, and I'm going to conclude the same thing, identical thing in fact, right. V dot is basically I can manipulate in such a way that V dot is going to be summation of this particular the Riccati equation part plus 1 minus 2 alpha by 4 with some non-negative quantity minus L1, and knowing L1 is positive, we can show that V dot is going to be strictly less than 0 for all x non-zero as long as alpha is greater than or equal to half. So that again guarantees gain margin of half infinity, right. So of course what one needs to understand here is I put some conditions that guarantee my answer, but in sometimes L1 can be non-negative, but in which case we need some kind of zero state observability condition and things like that. So, there are some generalizations to this result, but the summary is very simple. If my cost is of a particular form, L1 plus quadratic function in U, and L1 is non-negative or positive, and your main equation x dot is equal to f of x comma u is affine in U, then we can arrive at this particular Hamiltonian equation, which is the equivalent of your Riccati equation, which hopefully gives you the solution to your Lyapunov function, right? And but the nice thing is basically they guarantee gain margin of half infinity, right? So, like I was saying, in the finite horizon case, basically V is looked at as a value function, and then basically all the reinforcement learning methods actually try to estimate that in a real time based on the data and things like that. So, in that sense, some of these things can be generalized to those cases and solved, but this is a way to guarantee actually robustness and things like that. And to the best of my knowledge, I am not aware of other methods in terms of without going really analytical the way we show, right. So, anyway, that is gain margins for a general feedback controller, but we will now look at other types of stability margins, right. So, just as a quick reminder, let me go back and basically, I lost the file, but anyway. So, in classical control, we have a transfer function basically, and let's say some kind of controller. I don't know, I'm calling it C of S, and the assumption is basically we will end up with some kind of uncertainty here, right. If this delta is something like alpha times identity, that leads to gain margin. In scalars, there is nothing like identity, just alpha, right. So that sensitivity to something like a scalar real number is basically what we call as gain margin, whereas if you have something like e power j theta or something like that, then that leads to phase margin. Okay. I mean, it's much easier to understand what is gain margin. It is some kind of multiplicative factor that we are protecting the system against when it comes to controller. Imagine basically you're driving a car, and then let's say your control action is coming through accelerator or brake. Instead of putting exactly 1 degree or whatever the units that you want to use, let's say 1 centimeter is what we expect to push, but then we end up actually pushing 1.1. That's a multiplicative factor. Phase margin is a lot harder to understand. The electrical engineers came up with this concept basically where the input is actually phase shifted, and is it robust against such phase shifts. But there is actually another reason why people look at phase margin, that is, if you have time delays, then phase margin is one way of protecting the system against such time delays, right. And many of the controller design specifications involve phase margin specifications, and indirectly they are related to your time delays, right. So, we will consider the same affine in control dynamical system, and we assume that basically we already have some kind of stabilizing controller. This is not necessarily optimal to define stability margins. We just need an arbitrary stabilizing controller. Then we consider this uncertain system, just the feedback loop that we have seen for frequency domain, but you can imagine everything is replaced by time domain, and you exactly understand the same thing. So, I have this uncertainty delta, which could be an operator on the control that is coming in, right. So, basically delta is obviously some kind of uncertainty operator which belongs to some set bold delta, and the assumption is the bold delta has the identity operator, right. I mean, when bold the delta is equal to identity operator, we essentially get back the original system with phi of x as the stabilizing controller. So the problem is basically determining the largest set delta for which the zero solution is asymptotically stable for all delta, and that's essentially identifying the margins of this particular system with that particular feedback controller. So in this particular case, we say the system G and the feedback controller has a stability margin delta, but this is not still quantitative. So we will actually now define a very quantitative version of the margins, right? So for that, we will pick two numbers alpha and beta that satisfy, alpha is a positive number, beta, both are positive, but one is below 1 and the other one is above 1, right? So we say the system G and its feedback control phi has a gain margin alpha beta if G delta is asymptotically stable for all delta, where this delta is basically a matrix, diagonal matrix multiplying the control, right? So you have bunch of parameters, the diagonal parameters, and all those parameters have to be between alpha and beta. So that's the margin that we are talking about. If the system is stable for all such case between alpha and beta, then we call that it has a gain margin, right? I could have actually a matrix version, but this is the standard version, so we put it there. In fact, we will see in a second that in a certain fashion we actually generalize everything to something called disk margin in a second, right? And this is gain margin is typically just the multiplicative uncertainty, whereas one can actually imagine instead of simply a multiplicative factor, you could actually have an nonlinearity like in the absolute stability problem, and then we call that as a sector margin, right? Same thing. I mean, this system has a sector margin for that particular feedback controller if delta is given by a nonlinearity. Again, bunch of nonlinearities acting on each and every control input, and that nonlinearity satisfies this inequality, essentially thinking about the absolute stability problem, where we actually looked at stability with respect to sector uncertainties, right? Now both these things can be actually sort of generalized to something called disk margin, right? Using our favorite concept of dissipativity, where we assume that the operator delta will have input and output u sub c and y sub c. Now of course in this particular case, input is actually the u itself, and then output is basically whatever the output coming from this operator, which is actually going to be the input to your system. That will be your feedback control with the uncertainty delta. Anyway, so I'm going to assume that this delta operator is going to be dissipative with respect to this quadratic supply rate of a very specific kind in terms of this delta, alphas and deltas, sorry, alphas and betas. It looks awfully technical, but actually to understand it, you practically think of it as alpha and beta in these expressions, right? Just to give that daylight for getting asymptotic stability, we force ourselves to put some of these things. Anyway, so this disk margin allows systems of dynamic in nature. So that means this particular delta, the value, the control input is coming from phi of x or whatever, and that drives a dynamical system, and the output is what is going to be used as input to your basic system, and that becomes your modified control, so to speak. But this one is actually going through a dynamical system, and that dynamical system satisfies a dissipativity. So we have feedback interconnection in this particular case. I chose it to represent it as positive feedback, but could be very well represented as negative feedback. So we know this. If we have two systems in interconnection fashion, if one of them is dissipative, the other one has to be dissipative with some something like R plus RC is less than or equal to 0, or some scaled version of that, right? So it's as simple as that. But the nice thing is basically this particular notion of disk margin, if I pick slightly more specialized supply rate, I can actually specialize it to your sector margin and gain margin. So there are generalization to something called structured disk margin. It's not generalization, it's actually a specialization, so to speak. And then that structured disk margin is generalization of sector margin, and sector margin is nothing but a generalization of gain margin. So in that sense, if you understand disk margin or structured disk margin, then basically everything comes for free, right? So So disk margin implies structured disk margin, and structured disk margin implies sector margin, and sector margin implies gain margin, right? It's a trivial note that perhaps you guys can actually convince yourself that it is indeed true, right? It's a manipulation of some of these equations. Now, before I present any result in this particular category, what I'm going to say is basically if if we want phase margins, let's say, then this delta could be chosen as actually a delay operator. So I won't have time to basically discuss that probably in this particular case, but you can look at literature. Basically, some of the papers I've authored has this concept where the delay operator can be shown to be dissipative with respect to some supply rates and things like that, and then basically that guarantees some kind of phase margin and things like that. So this concept of disk margin sort of combines both gain and phase margins. In the special cases, it may give gain and sector margins, but actually has the inherent notion of phase margins embedded in it. So anyway, let's actually present the first result in terms of sufficient condition for guaranteeing disk margin. Remember, we already assumed that we have a phi of x that is stabilizing. So the result is something like this. We assume that basically there is some kind of Lyapunov function candidate V and L and W, right? These will remind you of your extended KYP conditions that we briefly went through at some point, such that the first equation is satisfied involving these alphas and betas, and of course the feedback control phi and some positive diagonal matrix Z, right? And then the second equation also involves L and W and Z and phi, right? And then same thing, the third equation, right? So these are actually special cases of your dissipativity sufficient conditions in terms of extended KYP. If you recall, a while ago we have discussed these KYP conditions coming from historically positive real, and then we showed that in the nonlinear case we can actually write those sufficient conditions and necessary. In fact, in certain cases they are necessary also, necessary and sufficient conditions for dissipativity of with respect to quadratic supply rates in terms of this extended KYP. And essentially I am writing those for this specific supply rate, right? If we can find such a V, right, we already assume that phi is stabilizing and things like that, then G and with the feedback controller has a structured disk margin alpha beta, and of course if Z is picked to be identity, then we can guarantee disk margin, right? So the proof is a direct consequence of KYP lemma, and then I think that could be a nice problem for you to solve, okay? And it so happens that disk margin, as I was saying, is kind of guarantees phase margin. In the case of linear systems, it's much easier. The concept of phase margin is not really expanded to nonlinear systems, though one can conceive, we can actually define artificially how that comes. But in the linear systems, at least the disk margin guarantees a phase margin of sum minus phi to plus phi, where cosine phi is given by this alpha beta divided by alpha plus beta, right? So it's nice to know that dissipative theory provides these three equations that guarantee disk margin, right? So what does this mean? We have phi of x, and if that phi of x along with its Lyapunov function or some other Lyapunov function for that matter satisfies these three equations, then we can guarantee structured disk margin and disk margins, right? And then eventually leading to gain and phase margins and things like that, okay? This set of three equations can be written as a single inequality. It should remind you of the Schur's complement theorem that we spoke a while ago. Basically, you can always take a bunch of inequalities, put them in a matrix, and then do this magic called Schur's complement. And please note that in many cases I'm dropping x simply just for the equation to look slightly clean, but in reality there's nothing to it. I mean, we all have x everywhere actually. Anyway, so the conclusion is going to be identical, except basically we got rid of these additional functions L and W, and we wrote it as a single inequality. And then this should remind you of your Riccati type of inequality, right? Riccati is an equation. Why is that Riccati type equation? So let's say, as far as we are concerned, basically phi is known, some stabilizing, and we are trying to find the storage function or a Lyapunov function in terms of this equation inequality that satisfies V prime. So suppose if you were to search for this particular V prime, you could use the previous equation, rewrite them as a matrix inequality or this quadratic inequality. In either way, basically we can use semi-definite programming to search for these V primes, and then once we have V prime, then we integrate it out and to get V, right? And hopefully that V actually satisfies the Lyapunov function conditions, right? Especially the positive definiteness and things like that. So you can actually put all those things together and then formulate this as a semi-definite programming using SOS tools, and that way we have a computational method of solving for disk margins, right? And therefore gain margins and phase margins and things like that. So like I said, there's nothing so deep about this beyond the fact that we use distributive theory and rewrote them as basically inequality in terms of this V prime and phi. Okay, so the previous result basically tells you how a particular phi guarantees certain margins. Here, on the other hand, we will actually do the opposite. Can we get some phi that guarantees a certain disk margin, right? So let me not really speak much more and then present the result. Basically, again, we'll always assume that some alpha beta are given, and then Z is a positive diagonal matrix. It could be any positive diagonal matrix. And if you have a Lyapunov function, candidate V of x, that means V of 0 is 0, V of x is positive for non-zero x, that satisfies this quadratic inequality in terms of V prime, right? Then with phi is equal to given by this particular expression, it guarantees a structured disk margin alpha and beta, and then if Z is picked to be identity, if this V can be found, V prime can be found with Z equals identity, then we can guarantee disk margin, right? So I want us to understand the difference between the previous result and this. In the previous result, I was given a phi, so I don't have a choice. So I actually looked for V primes that satisfies a certain equality, guarantees disk margin. Okay, then shows that the result that basically shows that phi of x actually ensures that you have a particular disk margin. Here, on the other hand, we are saying basically, look for a V prime that satisfies this inequality, and then we can actually design for phi that guarantees alpha beta, right? So both are kind of converse to one another, and eventually we'll see that this particular concept that we just used, we have some kind of inequality in terms of V, and that if it is satisfied, we can actually design a controller. So this is a nice way of designing controller. In this particular case, this is not optimal at all, but it has some disk margins. So it's a good result to have, right? So that brings us to the linear case, and then basically, so if we have this linear inequality, matrix inequality, quadratic matrix inequality in terms of P, then if you pick your feedback controller, linear feedback controller, to be minus gamma onto alpha plus beta, Z inverse beta transpose P, then we have a structured disk margin, right? So just to see how it works, right? It works out very well, and basically, as you know, this quadratic P can be written in terms of using Schur complements. You can write that as a linear matrix inequality. So by solving this linear matrix inequality and by picking K to be this, we get this structured disk margin. And I want us to understand, first we look for stability, and this is obviously going to be stronger than this. This implies stability anyway. So it's a good problem for you. Basically, if I have this particular condition, can I guarantee stability using our standard results that we saw before and things like that. So this is a stabilizing controller, but much more. It has actually disk margins and gain margins and things like that, right? So it's always nice to know that our nonlinear result specializes to something simple in the linear case, right? So now we will kind of end the discussion of this particular lecture, finally talking about quadratic costs, right? And then basically minimizing them, and then see if they have stability margins. And we have seen this already, so there's really not much. It's going to be a quick note in that sense. So if we consider the nonlinear system that has affine in control form, and we define this cost, except basically the previous cost that we chose at the start of the lecture is simply does not have this linear term in u. So I'm going to include the linear term. L1 of x is maybe non-negative, L2 of x is something times u plus the quadratic term, where the R2 that I have here I chose to be positive diagonal. You can generalize to the cases where it's not diagonal and it can be a function of x. The maths becomes a little bit crazier, so I chose not to give that, right? So we'll assume that there exists a V so that this equation is satisfied. What is this equation? This is the optimality equation. It is the Riccati extension to nonlinear system in terms of the Hamiltonian. So this is nothing but h of x comma phi comma v prime is equal to 0 equation. Okay, so don't think that this is anything different, except basically it has this L2 in it and things like that. So then it will not take much effort to show that u equals phi given by this particular thing is stabilizing and minimizing. So let me actually just pause for a second and basically convince you that this is indeed the case, right? So what I have here is x dot is equal to f plus gu, right? And then the cost is L1 x plus L2 u, L2 of x times u plus u transpose R to u, right? So your Hamiltonian therefore is going to be equal to L1 plus L2 u plus u transpose R to u plus P transpose times F plus GU, okay, which can be written as this: u transpose R to u plus L2 plus P transpose G u plus L1 plus P transpose F. Okay. So now it's clearly, since R2 is assumed to be positive diagonal, this is going to be again a strictly convex function, and then basically set partial h with respect to u is equal to 0, and that gives me something like 2 R2 u minus plus this entire quantity transpose. So that implies u equals minus half R2 inverse L2 plus P transpose G transpose. Okay. So and of course we can substitute that in this particular equation, and you will get the Hamiltonian, h of x comma phi comma p is equal to 0, and then of course if you subtract these two, and then you will get a quadratic function in terms of u plus this transpose R2 times that, and that's going to be non-negative, satisfying all the conditions that we have seen in the optimal regulator framework, and therefore this phi is going to be stabilizing and minimizing, right? Stability comes from the fact that V is Lyapunov function candidate. Okay, so now what we can further do is, if somehow we know that these R2s and L2s or L1s are such that this inequality is satisfied for some theta between 0 and 1, then we can guarantee a structured disk margin of 1 by 1 plus theta and divided by 1 by 1 minus theta, some disk margin or a structured disk margin, right? So I want us to understand, suppose if we didn't have this, what we call as cross term L2, suppose that's 0, then clearly this particular inequality that we have is satisfied for every theta, right? So that means it's satisfied for every number between 0 and 1. Okay, At 0, if you actually look at this particular disk margin is going to be 1 and 1, right? Both these numbers coincide with 1, and then that's the smallest disk margin possible. Obviously, we don't want to pick theta to be 0 in that particular case. If we can let this theta going to 1, then the left hand side number goes to half, the right hand side goes to positive infinity, right? So that recovers your standard half infinity gain margin, or disk margin for that matter. So this result is kind of a generalization what we have seen in the gain margin discussion at the start of the lecture, but with the cross term, and then basically in spite of the cross term we actually can get these disk margins and things like that, and then eventually gain margins and phase margins, right? The phase margins are going to be in terms of this alpha, beta and things like that. So this is your alpha and this is your beta, so you can do the math, and basically we'll get some kind of phase margin for each one of these things in the case of linear systems. Okay, so let's look at the illustrative example where x1 dot is given by this, and x2 is dot is given by this, and cost function is very simple. It's chosen to be quadratic. Okay, and we have this v of x to be chosen to be x1 square plus x2 square. Okay, this is your optimal regulatory equation, or the Riccati equation equivalent of nonlinear systems, and I'm claiming that basically v of x is going to be satisfying this, right? And it's a matter of simply substituting this. L2 is 0 in this particular case because there is no cross term here. L1 is simply this 2x1 square plus 2x2 square. R2 is 1, actually half. Okay, and v is given by this. F of course is everything but the u part, and the g is actually coming from 0 and x1, and substituted, right? And I welcome all of you to basically try this out, okay, and convince yourself that indeed this particular equation is satisfied, right? So we can get basically the feedback controller by substituting. R2 is half, so R2 inverse is 2, so that 2 cancels with that. V prime is whatever, G is 0x1, L2 is 0, so we'll get a very simple feedback controller, and everything here is actually polynomial, and interestingly one can try to solve this using things like semi-definite programming. It fits that framework, that's what I mean. So once we get that, basically since in this particular case actually L2 is 0, we automatically can show that the gain margins and disk margins, all of them are going to be half infinity. Okay, but otherwise the purpose of this particular example for you is actually to ensure that this particular optimality equation is satisfied, and computing the phi, and of course getting the stability margins for free, so to speak. Okay, so that brings to the end of this particular lecture. In the next class we will actually get back to this idea where in all these cases we saw solutions to optimal control equations, and then basically showed that they have margins. Sometimes we may not have that luxury, and then we end up with a case where we know that there is a feedback control law, we just don't know how to arrive it. But then once we arrive it, do they have margins? Do they satisfy some kind of optimality? What do they minimize, if at all they are minimizing something? So that concept is called inverse optimality. So for that we will introduce this concept of control Lyapunov function. It's kind of related to what we've been discussing, but it's kind of an independent topic where we'll give a formula for designing controllers if certain things are true in terms of this thing called control Lyapunov function, and once we have that, we can actually show stability margins and some kind of optimality criteria, right? So thank you, and I'll see you in the next lecture.